Hello everyone, welcome to my YouTube channel. Now we are going to explore radar data collection and imaging with synthetic aperture radar geometry and terminology. Let's start. Contents: SAR imaging geometry and terminology. Radar data cube. Circular SAR, CSAR, data collection geometry. 3D reconstructed image from Gocha data. Conclusion: SAR imaging geometry and terminology. Radar stands for radio detection and ranging. Radar imaging radar is commonly known as synthetic aperture radar, SAR. A radar system transmits a sequence of pulses on targets of interest that are reflected back into the receiver antenna. The receiver system records the echoed signal. The time delay between the transmit signal and the receive signal is used to calculate range information based upon the constancy of the speed of the propagation of radar pulses. The fundamental SAR imaging geometry is shown in Figure 1.1, where an aircraft carrying the radar flies a straight flight path or strip map mode with a velocity at a certain altitude. The slant range is the distance from the radar to the imaging scene center. The azimuth angle is defined to be the angle around the scene center, which encompasses 0 to 360 degrees. Azimuth angle is also known as aspect angle. The elevation angle theta is defined to be the angle measured from the ground plane toward the positive z-axis, which encompasses 0 to 90 degrees. The angle between the slant range delta and the ground plane is typically a measure of the elevation angle. Elevation angle is equivalent to the depression angle. Ground squint angle is the angle between the aircraft's flight path to the projection of the slant range on the ground. After radar data have been collected, raw phase history data, some preprocessing and image formation algorithms are applied to the data to form an image. The image formation algorithms could be as simple as range Doppler processing, to the more accurate polar format algorithm, or to the extremely accurate backprojection algorithms. These methods provide various imagery quality depending on the cost of computation. A side-looking airborne radar, SLAR, processing approach develops a 2D reflectivity map of the imaged area. The reflectivity is the illumination of targets where the high signal-to-noise ratio, SNR, backscattered signals are the bright spots in the radar images and flat smooth surfaces are shown as dark areas. The flight direction is denoted as azimuth, and the line of sight as the slant range direction. The azimuth resolution decreases as the range increases. For example, a 9.6 GHz X-band SLAR system with a wavelength lambda of 0.31 meters and a 1.77 meters antenna D has an azimuth antenna beamwidth theta A is as shown in the equation 1.1. The azimuth resolution dA is the smallest distance between two targets that can be detected by the radar, which is, for a range of A0 is equal to 17.1 m, as shown in equation number 1.2. The distance between the radar moving at constant velocity v and a point on the ground, described by its coordinates, x, y, z, is equal to x0, 0, delta h, with delta h equal to the local terrain height, is obtained by as shown in equation number 1.3. Where, assuming t is equal to t0 is equal to 0 is the time of closest approach, when the distance is minimum as shown in equation number 1.4. In terms of the platform height h. In general from 1.3, the distance R0 is much larger than Vt during the illumination time t, for which a scattering center point on the ground is interrogated with radar pulses. Radar imaging seeks to D imagery. The slant range resolution D is inversely proportional to the system bandwidth according to dr is equal to C0 by 2br, where C0 is the speed of light, br is the bandwidth, gigahertz, and the factor of 2 is due to the two-way path from transmission to reception. The bandwidth is related to the difference between the maximum and minimum instantaneous frequency for a given chirp signal transmission waveform. Assuming the transmitted waveform amplitude is constant during the pulse time tau and the instantaneous frequency is linear over a chirp rate kappa r, then the bandwidth is br is equal to kr tau. The radar transmits and receives the echo signal and stores the received signal. The azimuth resolution dA is provided by the construction of the synthetic aperture, which is the path length over which the radar receives echo signals from a given point target scattering center. With an antenna beamwidth theta A, the corresponding synthetic aperture length is given by LSA is equal to A R naught is equal to lambda by dA R naught. A narrow virtual beamwidth results from a long synthetic aperture theta sa is equal to lambda by 2 liters sa, leading to a high azimuth resolution, as shown in equation 1.6. Notice that a shorter antenna sees any point on the ground for a longer time, which is equivalent to a longer virtual antenna length and thus a higher azimuth resolution. The received echo signal data form a 2D data matrix of complex samples, where each complex sample is given by its real and imaginary part, thus representing an amplitude and phase value. One matrix dimension corresponds to the range direction, or fast time. A range line consists of the complex echo signal samples after being amplified, down converted to baseband, digitized and stored in memory. One other matrix dimension represents the azimuth, or slow time, as the radar acquires a range line whenever the signal travels a distance v.pri, pulse repetition interval. Thus, the return echoes from the illuminated scene are sampled in both fast time, range, and slow time, azimuth. A series of echoed radar pulses form a coherent processing interval, CPI, which is also commonly called a radar dwell. Each pulse within a CPI is sampled adequately to retrieve meaningful target information. Each sampled point of a pulse is known as range bin or range gate, which is often reselected to correspond to a resolution cell that is intrinsic to the details of the sensor collection system. Since a radar system samples a pulse as it arrives, the range bin is also known as fast time sample and range axis is also known as fast time axis, see figure 1.2. After sampling the first pulse, the next pulse is sampled and the process continues until the last pulse of the CPI is received. Hence, the pulse axis is known as slow time axis. Two-dimensional matched filtering in slow time and fast time is called SAR imaging, figure 1.3. Besides the collection of a straight path with SLAR, there is also circular SAR, figure 1.4, which enhances spot mode radar by focusing on a single point. The single point could be the target of interest. The radar-carrying aircraft moves along a circular path with radius r on the plane z is equal to z0 with respect to the ground plane. Thus, the coordinates of the radar in the spatial domain as a function of the slow time r, x, y, z is equal to r cos theta, r sin theta, z0, where theta belongs to minus pi, pi represents the slow time domain. As the radar moves along the circular synthetic aperture, its beam is spotlighted on the disk of radius. Note, it is radius r and diameter is 2r, however d is not used, centered at the origin of the spatial, x, y, domain on the ground plane, the target region's support. With a side-looking SAR, starting at 0, r, h, then the instantaneous distance for slow time t, type equation here, such that v is equal to omega t, is given in equation 1.7 as shown here. And the interferometric phase difference, IPD, is given in equation 1.8 as shown here, where lambda is the wavelength, dH is the height difference, Rs is the slant range, alpha is the depression angle, beta is the angle between the flight horizontal plane and the aircraft altitude. An example of CSAR is the Gocha data set, shown in figure 1.5. The Gocha data set is fully polarimetric and consists of 8 complete circular, 360 degrees, passes, with each pass being at a different elevation angle, theta, where the radar used in the Gocha data collection has a center frequency of 9.6 GHz, giving a center wavelength of lambda c is equal to 0.031 and a bandwidth of 640 MHz. Each pass has a planned, ideal, separation of d theta is equal to 0.18 degrees in elevation with a planned elevation theta belongs to 43.7 degrees, 45.0 degrees. Actual flight paths differ from the planned paths, with elevation varying as a function of azimuth angle. Given the parameters of ASAR data collection, then two common examples are aerial SAR and space-based SAR. The different altitude determines the range from which different resolutions result. For aerial systems, targets can be discerned, whereas for satellite imagery it is typically used for foliage and vegetation analysis. of data that support analysis including radar and electro-optical imagery such as laser, thermal, and visual data, Figure 1.7. The case for each sensor is based on the available sensors, the situation, and the mission of the sensor collection. Low-level information fusion, LLIF, includes the sensor data for object assessment including classification and tracking, whereas high-level information fusion, HLIF, incorporates the ability to understand the object assessment results over the situational context and sensor management constraints. Hence, information fusion includes many emerging concepts and more specifically opportunities for RF and EO image fusion. Imagery collection results in target exploitation. Target exploitation has a rich history designated as automatic target recognition, ATR. Conclusion. This presentation covered key SAR concepts, including imaging geometry, radar data cubes, and circular SAR, CSAR, collection. We saw how these techniques enable detailed 3D imaging, as demonstrated with Gocha data. Overall, SAR and CSAR provide powerful tools for capturing high-resolution radar images in various applications. This video content is sourced from Deep Learning for Radar and Communications Automatic Target Recognition book. Thank you and meet you in the next video.